Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us deep into the shadows of the universe, not the kind that hide behind your curtains, but the kind that drift silently between stars, shadows cast not by the absence of light, but by the presence of distant dangers, cosmic threats, invisible catastrophes, events that have shaped worlds, ended empires of life before ours ever began, and that still wait patiently in the folds of space. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the hidden perils of the universe together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Let's begin with a thought. When you look up at the night sky, perhaps from a porch, a balcony, or through a window late at night, there's a stillness that settles over everything. The stars seem so serene, tiny specks scattered across a velvet dome. They don't flicker in panic. They don't whisper warnings. They simply shine. And in that silence, it's tempting to think that space is peaceful, that the cosmos is quiet. But the truth is, the silence is deceptive. Above our heads, beyond the comfortable layer of air we call home, is a universe that is anything but still. It is a universe of explosions, collapses, storms of unimaginable scale, and objects so violent in nature that they defy direct experience. We tend to think of Earth as secure, protected, perhaps even insulated from such celestial chaos. But that's an illusion born of smallness, a result of standing on a planet that hasn't yet been erased. You see, cosmic time runs on a schedule we rarely consider. Human lifetimes are brief flickers. Even entire civilizations rise and fall in the span of geological seconds. And on that scale, our species is young, a newcomer at the galactic table. The Earth, in contrast, is old. It has spun through quiet and catastrophe for over 4.5 billion years. And in all that time, the threats from space have never stopped. They've just waited for their moment. Think of it like living in a quiet forest. For years, the air is still. The wind is gentle. The sun filters softly through the trees. But somewhere beyond the edge of your vision, a fire could already be burning. Or a sudden windstorm might be gathering speed on the other side of the mountain. The quiet, in these cases, is not safety. It's just the time before something changes. Earth's history is filled with scars. Not just the kind carved by tectonic plates and volcanoes, but the kind etched by falling rocks from the sky, by waves of radiation washing over the atmosphere, and by sudden chemical changes triggered by events so far away their origin stories are still unfolding. Some of these events have rewritten biology, others have nearly ended it. Yet here we are, alive, breathing, aware. We sleep beneath the stars, often without fear. We build cities with glowing roofs that hide the night. We fly in metal tubes through the upper atmosphere and rarely wonder if a wave of charged particles might be on its way. We have grown confident in a universe that is still largely unpredictable, but that's not a cause for panic. It's a cause for humility. Tonight our goal is not to stoke fear, but to gently illuminate. We'll walk through the kinds of threats that live quietly in the fabric of space, from gamma-ray bursts that could sterilize the surface of a planet, to rogue planets that drift silently through the dark like cosmic icebergs, invisible until it's far too late. We'll talk about asteroids, solar storms, volcanic moons, and the quiet dangers of magnetic fields that might one day flip, leaving us temporarily exposed to the full glare of the sun. And through it all, we'll reflect on what it means to exist on a small, fragile world in such a turbulent cosmic sea. Because in many ways, Earth is not just a planet, it's a survivor. It's made it this far not through immunity, but through timing, through luck, through an evolving understanding of the universe around it, an understanding we now get to be part of. So as you lie there tonight, listening quietly, perhaps with the weight of a blanket pulling you gently towards sleep, know that you are drifting through a galaxy that is very much alive, not in the biological sense, but in the dynamic, dangerous, ever-moving sense. Stars are born and die, planets collide, moons melt from within, radiation flies through vacuum like silent arrows, and yet, in all that movement, here you are, in this moment, safe, aware, floating softly in the pause between cosmic chords. Soon, we'll look more closely at these threats, one by one, not to fear them, but to better understand them, because understanding is a kind of comfort. It turns the unknown into a map, and even in the vastness of space, having a map, even a partial one, can be the difference between wandering and knowing where you are. For now, though, rest in the quiet truth that the universe is not peaceful, but you are, and that's where this story begins. There's something soothing about the steady turning of the earth beneath the sky. Day fades into night, night into day, and somewhere in the rhythm of that cycle, we learn to believe in continuity, in permanence, in safety. But Earth's past tells a quieter, deeper story, one written in ash, in craters, in the fossilized breath of vanished species. A story that begins not with warning, but with silence. Let's drift back for a moment, about 66 million years, to a world that thrived beneath a very different sky, the late Cretaceous. The air was warm, thick with ferns and pollen. Dinosaurs wandered across floodplains and forests. Oceans teemed with strange, toothed reptiles. Flowers were still a new thing, evolving alongside bees, and somewhere above, far beyond the clouds, a rock was falling toward Earth. It wasn't a dramatic descent at first. No trumpet of doom, no cosmic trumpet blast. Just a chunk of space debris, likely about 10 to 15 kilometers wide, hurtling through the void, travelling tens of thousands of kilometers per hour, drawn toward our planet by nothing more than gravity and timing. When it hit, the Earth didn't shatter, but the world changed forever. The impact struck near what we now call the Yucatan Peninsula, in modern-day Mexico, forming the vast Chicxulub crater. In less than a second, the energy released was greater than that of every nuclear bomb ever built, combined, multiplied many times over. The sky lit with fire, shockwaves raced through the crust, tsunamis thundered outward. A curtain of vaporized rock, soot, and molten material filled the upper atmosphere, blotting out sunlight for months, perhaps even years. The dinosaurs, those towering thunder-footed rulers of the Mesozoic, did not die in a single day. It was slower, more suffocating. Plants withered, food chains collapsed. The earth grew cold beneath a darkened sky, and by the time light returned, 3 out of every 4 species had vanished. The age of reptiles had ended, and a new story had begun. Not everything died, of course. That's the strange and beautiful thing about extinction. It is not absolute. Some creatures endured. Small mammals, those shivering, burrowing survivors, began to thrive in the absence of giants. Birds, the living relatives of some dinosaurs, took to the skies. Seeds lay dormant in the soil, waiting for sunlight to return. And over millions of years, from the ashes of one world another emerged. One that would one day hum with electricity, build cities, write music, and send telescopes into space. If you listen closely, the Earth remembers. It remembers not with words, but with stone. The layer of iridium-rich clay found in sedimentary rocks all over the world, an element rare on Earth, but common in asteroids, tells us that the sky once fell. The fossil record shows a sudden silence, a sharp drop in diversity. Whole lineages vanished, and then, slowly, cautiously, life tried again. Chicxulub wasn't the only impact, of course. Earth's surface is pocked with scars, though many have been smoothed over by wind, water and time. There's the Vredefoot crater in South Africa, nearly 300 kilometres wide and over 2 billion years old. The Sudbury Basin is in Canada formed by another enormous strike. More recently, the Tunguska event in 1908 flattened thousands of square kilometres of forest in Siberia, thankfully in a place where no cities stood. A warning shot, perhaps. These are not myths or ancient fears. They are geological facts, etched into the crust, preserved in the strata, waiting quietly beneath our feet. And they remind us that Earth is not merely a home. It is a participant in a vast cosmic lottery, and every so often it draws a losing number. But it's not only the impacts themselves that shape history, it's what comes after, the evolutionary reshuffling, the ecological resetting. When an asteroid crashes into the planet, it doesn't just end an era, it opens a door to something new. Mammals would not have inherited the Earth without Chicxulub. Humanity might never have emerged. There's a soft irony in that. Our very existence may be the byproduct of extinction. We are, in a sense, the children of catastrophe. And so, when we speak of cosmic threats, it isn't in the spirit of alarm, but of awareness. The sky is not out to harm us, but it doesn't know we're here. Gravity pulls, objects drift, orbits decay. The universe is neither cruel nor kind, it's simply vast, and in that vastness collisions happen. Sometimes they leave craters, sometimes they leave stories, and sometimes they leave us. Tonight, as we drift further into this gentle exploration, remember, the world beneath you has been broken before. It has burned, frozen, darkened, and cracked. But it has also endured. Life has found a way to begin again and again. Not always the same life, not always the same shapes, but something always finds a way to rise through the ashes. And as you lie here now, in a world of electricity, glass and glowing screens, you are part of that legacy. You are a voice in a long echo, reaching across time. You're made not only of stardust, but of survival. A species born in the aftermath of disaster, still looking up at the stars, not with fear, but with wonder. And yet, wonder includes knowing what came before, because Earth remembers, and so should we. If you've ever watched sunlight stream through the sky just after a storm, you've seen something close to a miracle. Not the light itself, which is ordinary in its abundance, but the fact that it makes it all the way down to your skin, passing through layers of atmosphere, bouncing off molecules filtered by gases, shaped by magnetism, and softened by clouds. It's easy to take this delivery of light for granted, as if it were always meant to be gentle. But Earth's safety is not a given. It's the result of a set of improbabilities, fragile alignments that act together as a kind of shield. The first layer of that shield is the atmosphere, a delicate veil of gases less than 1% the diameter of Earth itself, thinner relative to our planet than the skin of an apple. Within it are invisible components that make all the difference. There's nitrogen and oxygen, of course, but also traces of carbon dioxide, water vapour and ozone, each playing a subtle role. Ozone in particular acts like sunglasses for the planet. It absorbs the majority of the sun's most dangerous ultraviolet radiation, allowing plants, animals, and eventually civilizations to flourish under its protection. Without that thin smear of gas, the surface of Earth would be burned sterile. But the atmosphere alone wouldn't survive without help. That help comes from something you can't see, the magnetic field. Generated by the slow churn of molten iron in Earth's outer core, Our magnetic field extends far beyond the surface, creating a kind of invisible cocoon around the planet. It deflects charged particles from the sun, guiding many of them harmlessly toward the poles, where they light up the sky as auroras. It protects satellites, power grids, and, long before those existed, the fragile molecules of early life. You might picture the magnetic field as a kind of quiet guardian, humming softly in the background of existence. But like many quiet protectors, its presence is often unappreciated, until it fails. There have been times in Earth's history when the field has weakened or even reversed, its north and south poles switching places. During those times, the shield thins, and more radiation reaches the surface. Some reversals may have lasted thousands of years. Life persisted through them, but not always comfortably. The oceans, too, play a defensive role. They moderate temperature, store heat, absorb carbon dioxide, and act as a planetary buffer against sudden swings in climate. And they cover more than 2/3 of the Earth, making them not just a habitat, but a stabilizer. When asteroids strike, oceans can swallow part of the energy. When the sun flares, oceans dampen the extremes. They are vast, cold, deep, and quietly protective. Put all of this together, the air, the field, the water, and what you have is not a fortress but a delicate balance, a coincidence of traits. Earth is not uniquely designed for life. Life, rather, adapted to the environment that Earth happened to provide. And that provision has always been temporary. Here is where we begin to touch a deeper idea, one that has crept into the minds of physicists, biologists, and philosophers alike. It's called the Great Filter. Imagine for a moment the universe as a vast ocean filled with islands, planets, scattered like stones across time and space. Some of them may be capable of supporting life. A few might even nurture intelligence. But when we look into the sky, we don't see signs of them. No signals, no structures, no cosmic cities humming in the dark. Just silence. The Great Filter is one possible explanation for that silence. It suggests that somewhere along the path from dust to consciousness, there is a barrier, a kind of gauntlet that most civilizations do not survive. It could be the difficulty of life forming at all. It could be the step from simple cells to complex ones. It could be self-destruction through war or technology. Or it could be the universe itself. Maybe gamma-ray bursts erase young planets before they can flourish. Maybe rogue worlds, solar flares, or stellar deaths end fragile civilizations before they have a chance to call out. If that's true, then we, sitting here now with headphones on and sleepy thoughts wandering, may be among the very rare. Not because we are brilliant or special, but because we are lucky. Lucky to have formed when we did. Lucky to have a moon that stabilized our tilt. Lucky to have survived past collisions, past extinctions, past volcanic winters and atmospheric collapses. Lucky to live in a moment of relative calm, with telescopes instead of firestorms. This doesn't mean we're safe, but it does mean we're still here, and that in itself is extraordinary. So as we prepare to explore the more specific dangers that drift around us, the cosmic threats that haven't yet arrived but still could, keep this thought close. Earth is not safe by design. It's safe by chance. And every day that chance holds is a gift. We don't need to fear the universe, but we should respect it. And more than that, we should know it, study it, watch it, understand its moods and mechanisms. Because unlike the creatures that came before us, we now have the tools to see the dangers before they strike. We have satellites, sensors, simulations, and science. We can read the sky not just as a mystery, but as a map. Still, there are places on that map we've barely begun to chart. Up ahead are gamma rays, solar storms, asteroids, and wandering planets. Some will never touch us. Some may one day get very close. But all of them are real, and most of them, until recently, were entirely unknown. We live in a neighbourhood filled with quiet collisions, and we've only just learned how to listen for the footsteps. Let's listen together. If the universe were a grand stage bursting with fire and rhythm, then gamma-ray bursts would be the explosions that happen after the curtains fall. They are not the main act. They don't unfold slowly like a sunrise or a supernova. They don't wait for an audience. They arrive in silence, flash brighter than 1 trillion suns and vanish before anyone can react. And yet they leave a mark, not on the stars that birthed them, but on the unlucky worlds that happen to lie in their path. A gamma-ray burst, or GRB, is the most powerful explosion the universe has produced since the Big Bang. It's not a solar flare, it's not a cosmic ray, it's not a supernova, though it often comes from one. It is a narrow, focused beam of high-energy radiation, unleashed when certain massive stars collapse into black holes, or when two neutron stars spiral into each other and merge. For a few seconds, they release more energy than our Sun will in its entire 10 billion year lifetime. But the truly unsettling part of GRBs is not just their power, it's their aim. Unlike a supernova, which explodes in every direction, a GRB fires in a straight, focused line, like a lighthouse beam of death. If Earth were to find itself in the path of one of those beams, even from thousands of light years away, the consequences could be catastrophic. You wouldn't see it coming. Gamma rays travel at the speed of a light, which means there's no warning, no time delay, no red glow on the horizon. One moment, the world is as it was. The next, the sky flashes with invisible radiation. And what would happen then? Well, the burst itself wouldn't burn you like a fire. You wouldn't melt or vaporize, but your planet would suffer on your behalf. Gamma rays would strike the upper atmosphere and shatter nitrogen molecules, breaking them into reactive atoms. Those atoms would bind with oxygen to form nitrogen oxides, compounds that don't belong there. These, in turn, would attack the ozone layer, breaking it down, peeling it away. The ozone layer is our planetary sunscreen. It absorbs the sun's ultraviolet rays, keeping them from reaching the surface. Without it, every living thing on land, plants, animals, even the floating plankton in the oceans, would suddenly find itself exposed to ultraviolet radiation at levels the biosphere has never seen. Plants would wilt, DNA would fracture, skin would burn, food chains would collapse starting from the base, and unlike an asteroid impact, there would be no smoke or crater to mark the event. Just the slow, suffocating unravelling of the systems that hold life together. Scientists believe something like this may have happened before. Around 440 million years ago, during the late Ordovician period, Earth experienced one of its first known mass extinctions. A sudden, sharp cooling gripped the planet. Marine life, the dominant form of life at the time, began to die in massive numbers. Some researchers suspect that a nearby gamma-ray burst could have stripped away the ozone layer, altered the climate, and triggered a chain of changes that led to widespread extinction. We don't know for sure, but the clues are there, written into rock and fossil. Sudden extinctions, geochemical shifts, echoes of something immense and invisible. And how close would such an event need to be? That's the troubling part. A GRB within about 6,000 light-years could start depleting ozone. A burst from within 1,000 light-years could do severe damage. And if one occurred within 100 light-years, a tiny sliver of the galaxy, the effects could be devastating. Thankfully, GRBS are rare. In a galaxy of over 100 billion stars, only a few produce bursts, and fewer still aim those bursts in our direction. Most of the stars capable of producing GRBs are massive, fast-spinning and short-lived. More likely to be found in younger chaotic galaxies where star formation is still violent and crowded. Our own Milky Way is calmer now, older and quieter, and Earth's position, tucked away in a relatively peaceful spiral arm, offers some protection. Still, we've seen them, not here but out there. The Swift and Fermi satellites watch the sky every day, recording bursts as they appear. Some come from galaxies billions of light-years away. We've seen them light up detectors from across cosmic time. some from when the universe was just a fraction of its current age, brief, bright, and gone. In April of 2020, astronomers detected the brightest gamma-ray burst ever recorded, GRB 2041-5a, originating in our local galactic neighbourhood from a magnetar, a kind of neutron star with an absurdly strong magnetic field. It didn't hurt us. It wasn't aimed our way. But it reminded us that these events are not ancient or theoretical. They still happen, and sometimes they happen nearby. Yet we don't lose sleep over them. Not because they aren't dangerous, they are, but because there's nothing we can do to prevent them. There's no telescope that can detect gamma rays before they arrive. No shield we can build around the planet. No button to press to move Earth a few degrees to the left. When a GRB happens, we only learn about it once the burst has already passed through us, or missed us entirely. And so we monitor, we study, we learn. Not to stop the danger, but to understand it. Because understanding, even in the face of powerlessness, is a kind of strength. It transforms fear into perspective. It turns unknowns into stories, and in those stories we find meaning. The universe is not out to get us, but it is capable of tremendous force. And sometimes that force moves in straight lines, across vast distances, silently and without care, and we, brief visitors on a blue planet, just happen to be in the path, or not. Tonight, we're not in its path, and for now, that's enough. Stars, like people, are born, they live, and in time, though often far longer than our imaginations can comfortably grasp, they die. But unlike us, when stars die, they don't simply fade away. Some collapse quietly into white dwarfs, cooling over billions of years until their light is no more than a whisper. Others, the more massive ones, end with one final act of astonishing brilliance, a supernova. It is a death that doubles as a beacon, casting a glow across light years, sometimes bright enough to outshine entire galaxies, even if only for a few days. To see a supernova in the night sky is to witness the exhalation of a star's life, a release of everything it once was into everything that will follow. It is poetic, it is beautiful, and at times it is dangerous. Not all supernovae pose a threat to Earth. Our own sun is far too small to explode in such a way. It will one day swell into a red giant, swallowing Mercury, and Venus, and possibly grazing the Earth. But it will die gently in astronomical terms, shedding its outer layers like smoke rings before fading into a white dwarf. But the larger stars, those more than 8 times the mass of the Sun, carry within them a different fate. As they burn through their fuel, fusing lighter elements into heavier ones, they build up a core of iron, an element that, unlike the others, does not yield energy when fused. When fusion stops, the balance between outward pressure and inward gravity collapses. The core implodes, the outer layers explode, and in less than a second, a star becomes a memory. This is a supernova. From a safe distance, it's a cosmic fireworks show. But if one were to erupt too close to Earth, say within 30 to 50 light years, the results could be catastrophic. Like gamma-ray bursts, supernovae unleash a flood of high-energy radiation. While less narrowly focused than a GRB, a nearby supernova could still flood the Earth with X-rays and gamma rays, disrupting the ozone layer, altering atmospheric chemistry, and possibly contributing to mass extinctions. It's happened before. Roughly 2.6 million years ago, something changed in the Earth's environment. A subtle, yet significant deposition of iron-60, an isotope that doesn't occur naturally on Earth, began to appear in deep-sea sediments and Antarctic ice cores. This isotope is forged in the furnace of supernovae, and its presence here suggests that, not so long ago, in the quiet timeline of the Earth, a supernova occurred close enough for its debris to reach us. It didn't end life, but it may have altered the climate. Some scientists speculate it could have triggered glaciations or helped drive species into new environments. Others wonder whether these changes helped nudge early hominins onto evolutionary paths that eventually led to us. A supernova can do that, shift the board just enough to change the game. And what exactly would happen if one went off tomorrow, closer than before? If it were close enough, we might notice a strange light in the sky. A new star that appears suddenly, shining brighter than Venus. It would not twinkle. It would burn steadily for days, even weeks, casting shadows at night. That would be the visible part, the part we could admire. But the invisible part would be arriving too. A flood of neutrinos, nearly massless particles that pass through everything, would reach us first. Billions of them flow through your body every second already, harmless and ghost-like, but a nearby supernova would increase that flow dramatically, with uncertain effects on the delicate balance of Earth's upper atmosphere. Then would come the radiation, X-rays and gamma rays, disrupting electronics in orbit, altering the chemistry of the air, weakening the ozone layer. Over time, this could lead to higher ultraviolet levels, stressing ecosystems from plankton to forests, and with that stress would come uncertainty, evolution, extinction, and perhaps renewal. Still, there's no need to panic. Supernovae of the dangerous sort are rare, and space is vast. The closest star likely to explode anytime soon is Betelgeuse, a red supergiant in the constellation Orion. It's a bloated, aging star pulsing with instability. In late 2019 and early 2020, it dimmed significantly, sparking speculation that its time had come. Telescopes around the world turned their eyes toward it, watching for the end. But Betelgeuse did not die, at least not yet. When it does go, whether tomorrow or in 100,000 years, it will likely be a spectacle, but not a threat. At around 642 light-years away, it's too distant to harm us with its radiation. But it will still be a reminder that even the most ancient, most massive things in the sky are not forever. There are others, of course, Antares, Rigel, and stars we haven't yet studied in quiet corners of the Milky Way. Most are distant enough that their final breaths will be beautiful, not destructive. But we watch them just the same, not out of fear, but out of reverence. Because to watch a supernova is to witness the cycle of creation. The moment when a star in dying seeds the cosmos with elements that will one day form planets, and maybe, if the conditions are right, life. In fact, much of your body, the calcium in your bones, the iron in your blood, the oxygen in your breath, was forged in ancient supernovae, scattered across space long before the Earth was born. You are quite literally the echo of dying stars, and perhaps that's why their stories still matter to us. Not because they threaten us, though some might, but because we come from them. We carry their endings inside our beginnings. So, when you next gaze at the stars, remember that even in the stillness of the night, some of those points of light are already gone. Their last acts are only just arriving. Their echoes still ripple through space and through you. And when the next one comes, whether near or far, we will be here, listening, learning, and quietly grateful that we are not closer. In the dark heart of some galaxies, not all, but enough to make the universe feel slightly more haunted, something ancient and patient sits at the centre. Not a sun, not a star cluster, not a swirling storm of gas, but a mouth, a gravitational mouth, with no lips and no voice, that swallows light, time, and even certainty itself. We call them black holes, and though we often imagine them as quiet, hidden engines of destruction, some of them, when fed just right, become something even stranger. They don't just consume, they also spit. Let's begin where most things end, with collapse. When a massive star, far more massive than our Sun, exhausts its fuel and goes supernova, its core can collapse beyond the point of atoms, beyond the structure of space, until it becomes a singularity, a point of infinite density and zero volume, wrapped in a veil of no return known as the event horizon. This is a black hole, a region where gravity is so strong not even light can escape. It doesn't suck things in like a cosmic vacuum cleaner. Instead, it waits. If something crosses the edge, it falls in, quietly, inevitably. But there's a peculiar twist. Not all black holes are silent. Some, especially the supermassive ones that sit at the centre of galaxies, including quietly the one in ours, have a tendency to light up when they feed. When gas and dust spiral inward, they don't fall in all at once. They swirl around, forming what's known as an accretion disk, a hot glowing whirlpool of matter heating up from friction and radiation. In some cases, that disk doesn't just glow, it roars. Magnetic fields twist through it. Particles accelerate to near the speed of light. And from the poles of the spinning black hole, something incredible happens. Beams of matter and energy erupt outward. These are relativistic jets, columns of plasma and radiation that shoot out into intergalactic space, sometimes for thousands, even millions of light years. These jets are not gentle. They are not beams of light. They are more like rivers of radiation, narrow but immense, focused by magnetic fields and launched at speeds that bend the fabric of reality itself. They can strip gas from galaxies. They can sterilize regions of space. They can carve out cavities in the interstellar medium, vast bubbles where star formation is stunted or stopped altogether. And if one were pointed at Earth, well, that's where the poetry ends and the physics begins. If our planet were unlucky enough to be in the path of an active black hole jet, the experience would be something like being hit by the invisible tip of a cosmic flamethrower. The radiation would arrive without warning. Gamma rays, X-rays, high-energy particles, enough to damage the ozone layer, disrupt DNA, and trigger a chain of ecological collapse similar to that of a gamma-ray burst. The beam wouldn't have to be close. Even from tens of thousands of light years away, the focused energy could be enough to matter. But here's the good news. Earth is not near any currently active black hole jets. The supermassive black hole at the centre of our Milky Way, Sagittarius A star, worries quiet. It feeds slowly, gently, without the drama of jets. Other galaxies like M87 have visible jets, but they're not aimed anywhere near us. For now, the cosmic monsters are dozing. Still, their existence is worth contemplating, because they remind us that the universe has structures and behaviours that dwarf not just our understanding, but our imagination. Black holes are not anomalies. They are common. They are natural outcomes of stellar death and galactic evolution. And their jets are not freak accidents. They are, under the right conditions, inevitable. Even now, astronomers scan the skies using radio, telescopes to map the shapes of these jets, to understand how they form and what they mean. We watch distant galaxies like Centaurus A and 3C273, marvelling at the long, narrow threads of energy stretching across the void. We study quasars, the most luminous objects in the universe, and realise that they too are powered by black holes, lit from the frenzy of matter falling inward and the fury of jets exploding outward. And in the midst of all that observation, we remember our place. We orbit quietly. We do not shine like quasars. We do not spit fire into the void. We are a pale, temperate world tucked away in a quiet spiral arm, far from the galactic core. And perhaps that is why we're still here. Had our solar system been born closer to the centre, where stars are crowded and black holes feast, we might not have lasted long enough to notice. A jet could have passed through long ago, long before mammals, long before microbes. If Earth had ever been in the path of such a beam, it's likely we would not be having this conversation at all. But we are, and that's worth something. Because while the monsters feed in the dark, we learn to read their stories in the light. We map the jets, we name the galaxies, we measure the curvature of gravity and the flicker of particles. And though we cannot yet prevent their fury, we can understand it. And sometimes, understanding is the first kind of protection. So if you find yourself staring at the stars tonight, wondering whether something immense might be staring back, you're not alone in the thought. But rest easy. Not because there's nothing out there, but because for now the most dangerous things are far away and not looking our way. and while they feed, we dream. There are moments when the universe seems to hold its breath, not because something quiet is happening, but because something so intense, so improbable, so tightly wound in the fabric of matter itself is about to unfold. Neutron star collisions are like that. They are the soundless symphonies of cosmic violence. Compact stars, each no larger than a city but heavier than our sun, spiralling toward one another in a fatal dance that ends with a burst of energy, bright enough to be seen across galaxies, and a shower of elements that might someday become rings on fingers or wires in circuits. To understand why these events matter, and why they belong in any conversation about cosmic threats, we have to take a step back and look at what neutron stars really are. When a massive star explodes in a supernova, it sometimes leaves behind a remnant. If the star wasn't quite massive enough to collapse into a black hole, it may instead compress into a neutron star, an object so dense that a single teaspoon of its material would weigh about 1 billion tons. This isn't just heavy, it's incomprehensibly packed. The atoms themselves are crushed, their protons and electrons squeezed into neutrons. It is, quite literally, a star made of nothing but the collapsed cores of atoms. And sometimes, by chance or by the quiet arrangement of binary systems, two neutron stars find themselves locked in orbit around one another. Slowly, over millions or billions of years, they spiral inward, radiating gravitational waves, losing momentum, tightening their path, until finally they collide. What happens in that moment is still being studied, but we know this: it is not subtle. The collision releases a burst of gamma rays, similar in form though generally shorter-lived than those from collapsing stars. This is what we call a short gamma ray burst. For a few milliseconds it outshines entire galaxies. At the same time, space itself ripples. Gravitational waves, distortions in the very geometry of reality, propagate outward like the ripples from a stone dropped in a pond, except the pond is space-time, and the ripples are moving at the speed of light. It was only recently that humanity became capable of detecting these ripples. In 2015, the LIGO observatory in the United States, and later the Virgo detector in Europe, began capturing evidence of gravitational waves. Then, in August 2017, something extraordinary happened. For the first time, a gravitational wave signal was detected, and it came not from black holes, but from the collision of two neutron stars. Almost simultaneously, satellites recorded a gamma ray burst. Telescopes around the world turned to the source, watching as a new kind of supernova-like flare appeared, spreading heavy elements into the cosmos. It was a breakthrough, a confirmation, a moment of scientific awe. But it was also a reminder of just how powerful and potentially dangerous these events can be. If a neutron-star collision occurred too close to Earth, the consequences could resemble those of a gamma-ray burst. Damage to the ozone layer, increased radiation, disruptions to climate and life. The likelihood is low. Most such events happen far from us, and the odds of Earth being in the direct path of their radiation are even smaller. Still, the danger isn't zero. And what's more haunting is that we wouldn't know until it had already happened. But the threats are not the only reason we care. Neutron star collisions are also the forges in which the universe makes its heaviest elements. Gold, platinum, uranium. These are not made in the cores of normal stars. They require something more dramatic, something more violent. The shock waves and neutron-rich environments created during these mergers provide the perfect conditions for rapid neutron capture, a process known as the R process. It's here that atoms are stitched together in the crucible of destruction. That gold necklace, those platinum circuits, those ancient specks buried in the Earth's crust? They were born not in silence, but in crashing stars. They were carried across space, embedded in dust, caught in the collapse of the solar nebula, and finally gathered into the young Earth. Everything precious, everything rare, forged in the flash of gravitational violence. In this way, the terrifying becomes the beautiful. And as with so many things in the cosmos, what can destroy can also create. A neutron star collision might erase a world, but it can also seed another with the elements it will need to one day bloom. So where does that leave us? It leaves us with wonder mostly. With the knowledge that the universe, while vast and unknowable in many ways, has rhythms and patterns that we are slowly beginning to detect. With instruments sensitive enough to measure vibrations smaller than a proton, we now hear what was once silent. We can watch the sky not just in light, but in waves of gravity. We're eavesdropping on cataclysms and we're doing it gently. And while we listen, we remember that not all threats wear a familiar shape. Some are not comets or flares or planets out of place. Some are the quiet convergence of two stars, unseen and unheard for millennia, until at last they touch. And in that moment, the universe takes a breath, and then lets go. Earth has not yet been close enough to feel the worst of such a collision. But it might someday, or it might never. Either way, the sky holds the memory of these events, just as Earth holds the memory of its own past traumas. And now, we hold that memory too. Tonight, as you lie beneath the stars, or beneath your ceiling, picturing them, know that the universe is still playing its quiet music. Somewhere, two stars are spiraling closer. Somewhere else, the heavy elements of their collision are drifting through space, carried on dust, waiting to become something new. You're made of many things. Stardust, yes, but also the remnants of crashing stars. You are, in a way, the echo of a collision that didn't kill, but created. And that too is something to sleep on. Not every threat comes with fire. Some drift slowly, soundlessly, across the dark. They do not roar or flash. They do not announce themselves with tails of ice or storms of radiation. They do not aim, and they do not care. Rogue planets, worlds without stars, move through the galaxy like lost shadows, invisible until they are much too close. They are the cosmic equivalent of icebergs in a night sea, immense, silent, and almost undetectable until you've already felt their pull. Unlike the planets in our solar system, which dance in orderly orbits around the sun, rogue planets are untethered. They are planets that have been flung out of their solar systems, cast adrift by gravitational chaos. Maybe their host star died and destabilized the system. Maybe a close encounter with another planet or a passing star ejected them into deep space. Or maybe they never had a star to begin with, forming in isolation from gas clouds dense enough to collapse into a planet, but not massive enough to ignite fusion and become a star. Whatever their origins, the result is the same: a cold, dark world wandering through the interstellar void. And there may be more of them than we ever imagined. Recent studies suggest that rogue planets might actually outnumber stars in our galaxy. Some estimates propose that for every star, there could be one or even several rogue planets drifting in the dark. That means hundreds of billions of these invisible giants could be out there, scattered like marbles across a vast and empty floor. Most of them will never pass near us. Most will glide through space without incident. But the universe is big, and time is long. Given enough of both, even the rarest alignments become possibilities. What would happen if one came too close? The danger of a rogue planet is not that it would collide with Earth. Space is too vast for that to be likely. The true risk is gravitational. If a rogue planet passed through our solar system, even at a considerable distance, it could disrupt the orbits of the planets. Like a heavy stone dropped into a still pond, its gravity would ripple outward, tugging at the delicate balance that keeps our worlds in place. It might nudge an asteroid onto a collision course with Earth. It could stretch or compress Earth's orbit, altering our seasons or destabilizing our climate. It might even capture smaller moons, or send them spiraling away. In the worst-case scenarios, rare, yes, but not impossible, it could trigger a chain reaction of orbital chaos. Planets shifting, asteroids raining down, comets redirected. A slow unravelling of the solar system as we know it, and we wouldn't see it coming. Because rogue planets do not glow. They do not shine with reflected light unless they happen to pass near a star, which they almost never do. They are black against black, invisible to most telescopes. Only the most sensitive infrared surveys or the indirect motion of stars they pass near can betray their presence. By the time one approached the solar system close enough to notice, to see its effect on distant comets, on long-period objects at the edge of the Oort cloud, it might already be altering the quiet choreography of our world. Of course, this isn't likely. We have no evidence that a rogue planet is approaching us now, or that one has ever passed nearby in the history of complex life. But the absence of evidence is not quite the same as safety. It simply means we've had good fortune, or that the universe hasn't yet rolled those particular dice. There's a curious irony here too. Rogue planets may be lifeless rocks, or they may harbour strange forms of life. Some scientists speculate that massive rogue planets, with thick hydrogen atmospheres, could trap internal heat from their formation, creating warm, pressurized environments beneath layers of gas and ice. Far beneath their surfaces, where geothermal energy still lingers, there might even be liquid oceans, dark, deep, and utterly alien. If so, then these silent wanderers may not only be threats, they might also be homes. Some theories about the origin of life suggest that it doesn't need sunlight, only chemistry, warmth, and time. If that's true, then rogue planets, despite their isolation, might carry microbes or even more complex life forms within them. In drifting through interstellar space, they may serve as seeds, spreading potential across the galaxy without even trying. The same object that could, in the right circumstances, destabilize our planetary system, could also be a vessel of life. That's the universe for you. The same structures that end one thing often give rise to another. Tonight, if you think of rogue planets, don't picture them as missiles or monsters. Picture them as possibilities. Yes, they are threats, rare, cold, silent, but they are also reminders that not everything dangerous announces itself, and not everything that drifts in the dark is empty. Somewhere out there, between stars, a world without sunrise is floating through the black. It may never come close to us. It may never be seen. But it's out there, and it's moving. Not toward us, necessarily, but through the same galaxy, under the same physical laws, across the same shared fabric of space. It is not aimed, it is not malicious, but it is real. And the quiet part of the universe, the part we rarely look at, is filled with things like it. Some threats don't crash, they drift. And sometimes the most important thing we can do is remember to keep looking. Sometimes danger comes from above, and not in the form of poetic metaphor. It arrives in the shape of a rock older than any mountain, colder than any winter, and moving faster than any machine we've ever built. Asteroids are not science fiction. They are not cinematic spectacles. They are facts, stones in space, some small, some vast, some passing peacefully, some arriving with a force to change history. Earth wears its history like scars. Most of them have faded, weathered by wind and time, buried beneath oceans or forests or cities, but the story is still there, if you know where to look. One of the most famous scars lies hidden beneath the Yucatan Peninsula in Mexico, the Chicxulub crater. 66 million years ago, a rock more than 10 kilometers wide struck the Earth with a violence beyond human experience. The impact released energy equivalent to billions of nuclear bombs, vaporized everything within hundreds of kilometers, and launched enough debris into the atmosphere to blanket the skies and smother the planet's climate for years. It was not just an explosion. It was a punctuation mark at the end of an age. Dinosaurs vanished, forests changed, oceans emptied, and in the silence that followed, mammals began to rise. We walk in the shadow of that impact every day. But Chicxulub was not the only one. In 1908, something exploded over a remote region of Siberia known as Tunguska. The blast flattened trees across 2,000 square kilometers. Witnesses described a sky that burned. Though no crater was found, scientists believe a small asteroid or comet fragment, just 50 to 60 meters across, entered the atmosphere and detonated with the force of a large nuclear bomb, high enough to leave no impact crater, but low enough to devastate the land below. In 2013, it happened again, though on a smaller scale. A 20-meter-wide meteor entered the atmosphere over Chelyabinsk, Russia. It exploded mid-air with a shock wave that shattered windows across 6 cities and injured over 1,000 people. The event caught scientists off guard, not because they didn't know it could happen, but because this particular rock had gone unnoticed until it arrived. These are not fables. These are recent events, recorded with photographs, video, seismic data, and the memory of those who heard the sky crack open. So how many more are out there? Thousands. NASA tracks what are called near-Earth objects, asteroids and comets that orbit close enough to potentially intersect Earth's path. Of particular concern are those larger than 140 meters across, large enough to destroy a city or region. These are sometimes called city killers. As of now, more than 850 of them have been catalogued, and new ones are added regularly. The work is ongoing, tireless, and meticulous, but it's far from complete. One of the most well-known NEOs is Apophis, named after the Egyptian god of chaos. In 2004, astronomers observed its orbit and noted a small, but real, chance that it could strike Earth in the year 2029. Later calculations reduced that risk, but a new possibility emerged. If Apophis were to pass through a narrow gravitational keyhole, a tiny region of space just a few hundred meters wide, its orbit could shift in such a way that it might return for a collision in 2036. Again, more refined measurements calmed that fear, but the idea remains unnerving. Not just that an asteroid could hit us, but that a change as small as a keyhole, a corridor in space barely the width of a stadium, could determine our fate decades later. That's the kind of precision the universe deals in. Tiny changes with massive consequences. Cosmic billiards. So what can we do about it? Until recently the answer was not much. We could observe, we could track, we could predict, but we couldn't act. That began to change in 2022 when NASA launched the DART mission, the Double Asteroid Redirection Test. Its goal was simple in concept and groundbreaking in execution: to deliberately crash a spacecraft into an asteroid and measure whether the impact could alter its trajectory. The target was Dimorphos, a small moonlet orbiting a larger asteroid named Didymos. In September 2022, DART successfully collided with Dimorphos, shortening its orbital period by more than half an hour, a clear demonstration that, in theory, we could nudge a threat off course. It was humanity's first attempt at planetary defense. It won't be the last. Other space agencies are joining the effort. New telescopes are being developed to detect smaller NEOs, earlier and more accurately. There are proposals for laser ablation, kinetic impactors, even gravitational tractors, spacecraft that would hover near an asteroid and gently pull it off course using nothing but mass and patience. We're not powerless, not anymore. But we are still learning. We are still searching the skies. And that's what this part of the story is really about. Not just the rocks themselves, but the quiet race between detection and disaster, between knowing and not knowing, between the calm of today and the possibility of tomorrow. Because the sky is full of stones, some small, some large, most harmless, but some, just a few, are reminders that Earth does not exist in isolation. We live in a moving system, orbiting a moving star, within a moving galaxy. And in all that motion, paths cross, and sometimes when they do, the world changes. So tonight, as you rest beneath a roof, or under the stars, or simply within the thin protection of Earth's atmosphere, remember this: we've been hit before, we will almost certainly be hit again, but this time, we're watching. And that perhaps is enough to tilt the odds just a little in our favour. It's comforting to believe that if something dangerous were heading our way, we'd know about it. That with all our telescopes and satellites, with all our data and algorithms, we'd spot the threat long before it arrived. Warnings would go out. Experts would act. The story would end not with impact but with relief. But space doesn't always give us that courtesy. And the truth, quietly unsettling, is that even now, with all we've built and all we've learned, we're still missing things. You might imagine a cosmic watchtower, always scanning the skies, logging every pebble and mountain that might wander near our orbit. But in reality, our surveillance is patchy. It depends on timing, technology, and sometimes just luck. Some asteroids arrive from the direction of the sun, hidden in its glare until they're already upon us. Others are too small to be picked up by current surveys until days, or even hours before closest approach. In July 2019, an asteroid the size of a football field, later named 2019 OK, passed just 70,000 kilometers from Earth, closer than the Moon. It was only detected a day before its flyby. Had it been on a collision course, there would have been no time for deflection. Perhaps a warning, perhaps an evacuation, if it had been aimed at a city. But nothing more. It wasn't the first, it won't be the last. And while larger asteroids, those a kilometre or more in diameter, are more easily spotted and catalogued, the smaller ones, which still carry the potential for regional devastation, often slip through. A 50-metre rock, like the one that may have caused Tunguska, is nearly invisible unless it reflects light just right, at just the right time, in just the right place in the sky. Even with our best efforts, we're blind to many of them, and even when we see them, predicting their exact paths is an ongoing challenge. Asteroids do not move in straight lines. They're influenced by gravity, not just from the sun and planets, but from each other, from tiny tugs and nudges, from thermal effects like the Yarkovsky effect, where sunlight causes one side of a rotating asteroid to heat up and emit radiation unevenly, creating a minuscule but persistent push. Over decades or centuries, such pushes can alter an asteroid's path in ways that compound, making long-term predictions fuzzy. And this, perhaps, is the heart of the matter. Space is not a chessboard. It's not neatly gridded, predictable, and governed by straightforward rules. It's more like a flowing river, filled with eddies, drifts, and sudden bends. The idea that we can see every threat in time is comforting, but not accurate. Most sky surveys rely on nighttime observation, which means they miss half the sky at any given moment. Clouds and weather interfere. Funding limits the number and reach of telescopes. The southern hemisphere, vast and underwatched, leaves gaps in our coverage. Even space-based telescopes like NEWIC have limited lifespans and fields of view, and while efforts are underway to fix these gaps, with projects like the upcoming ENIO Surveyor mission and the Vera C. Rubin Observatory, the reality is that we are still playing catch-up with the cosmos. We can't protect what we can't see. That phrase has become a kind of refrain in the planetary defence community, not one of despair, but of purpose. It reminds us that our safety doesn't lie in strength, but in sight, in awareness, in knowing early enough to do something meaningful. But it also reminds us of the role of chance. So much of Earth's history, and our continued survival, has come down to timing, the angle of approach, the speed of rotation, the position of Earth in its orbit on a particular day. If the asteroid that struck Chicxulub had arrived a few minutes earlier or later, it might have landed in deeper water, altering the dust cloud and perhaps sparing some species. If 2019 OK had shifted slightly, we might be telling a different story right now. Chance doesn't just affect ancient history, it still rules the sky. And that is a difficult truth to sit with, especially in a world where we value control, where technology promises foresight, and where knowledge is often mistaken for power. But maybe the universe isn't about control. Maybe it's about respect. We respect the sky not because we fear it, but because we understand that it is larger, older, and more complex than we are. We build telescopes not out of paranoia, but out of curiosity and care. We run simulations not to predict the future perfectly, but to give ourselves the best odds of meeting it with preparation. And still, sometimes the unexpected arrives. The trick is not to panic. It is to learn, to keep watching, to accept that even as our knowledge grows, our blind spots remain. And in that acceptance, something gentle emerges. We become more alert. We become more humble. We recognize that Earth is not a fortress, but a boat. Beautiful, fragile, and floating through a sea that is mostly calm, but occasionally wild. And like all travellers, we depend on charts, on lookouts, on luck. The sky is vast and the map is still incomplete. But night by night, pixel by pixel, we're drawing it. And that perhaps is enough. The sun is a giver. Its light warms our oceans, fuels our forests, and paints our mornings gold. It drives photosynthesis, carves shadows across the land, and gives shape to time itself. But like many givers in nature, it also has moods. And every so often, the same star that nurtures life on Earth reminds us that it is not a quiet lamp in the sky. It is a roiling sphere of plasma, governed by magnetism and fury, and sometimes it lashes out. What we call solar storms are not storms in the earthly sense. There's no rain, no thunder. Instead, these are vast eruptions of energy and charged particles, hurled outward from the sun's surface into the solar system. They come in different forms. Solar flares are sudden flashes of radiation. Coronal mass ejections, CMEs, are enormous bubbles of plasma and magnetic fields launched into space. And while the Earth is protected by its magnetic field, these events can still reach us, and when they do, they remind us just how delicate our systems are. The most famous example is the Carrington event of 1859. On a late August morning, the British astronomer Richard Carrington was observing sunspots through a solar telescope when he saw a blinding flash of light. It lasted only a moment. But hours later, the Earth trembled, not physically, but electromagnetically. Telegraph lines sparked and caught fire. Operators were shocked through their equipment. Some systems continued to work even after being unplugged, powered by the electric storm in the sky. Auroras, normally confined to the polar regions, appeared as far south as Cuba and Hawaii. People woke in the middle of the night, thinking it was morning. The sky shimmered in unfamiliar colours, and no one could explain why. At the time, the world was only beginning to understand electricity. There were no satellites, no power grids, no dependence on digital communication. The damage, though dramatic, was limited. But what if a storm like that happened today? It's not a rhetorical question. We know, with certainty, that the sun produces such storms. We've observed them. And while not every CME is aimed at Earth, the ones that are can have wide-reaching effects. If a Carrington-level event struck us now, the consequences would unfold in layers. First, satellites would be affected. Many could be damaged or destroyed by radiation. GPS signals could be disrupted. Communication relays might falter. Some satellites, especially those without adequate shielding, could be permanently lost. Next, the electrical grid. A powerful geomagnetic storm induces currents in long conductors, like the power lines that carry electricity across continents. Transformers, which are difficult and time-consuming to replace, could overload and fail. In 1989, a relatively minor storm caused a 9-hour blackout in Quebec. A stronger storm could knock out power to large regions for days, weeks, or even longer. Aviation would also be affected. High-altitude polar routes could be flooded with radiation, forcing flight paths to shift. Astronauts on the International Space Station would need to shelter in shielded modules. Some scientists estimate that the economic damage from a severe solar storm could reach trillions of dollars, with cascading effects across supply chains, communication, and even food distribution. And all of this, all of it, could begin with a flare of light from a star we see every day. But it's not all helplessness. We're not just waiting to be surprised. In recent years, solar science has advanced dramatically. We've learned to study the surface of the sun in detail, to track sunspot cycles, to observe magnetic field lines twisting and snapping. We've launched missions to understand solar behaviour more intimately than ever before. The Parker Solar Probe, launched in 2018, is currently flying closer to the sun than any spacecraft in history. It dips into the corona, the sun's outer atmosphere, collecting data on solar wind, particle acceleration, and magnetic dynamics. The Solar Orbiter, a mission by the European Space Agency with NASA collaboration, provides high-resolution images of the sun's poles and surface, mapping its moods from afar. Together, these missions form the basis of what might one day become a space weather forecast. Not unlike the weather reports we check each morning, but for the solar wind instead of rain. The goal is not to stop solar storms. We can't do that. But with enough lead time, we can protect systems. Satellites can be put in safe mode. Power grids can reduce load or reroute electricity. Flights can be diverted. Spacewalks can be postponed. Like with hurricanes or earthquakes, preparation doesn't prevent the storm, but it can lessen the impact. Still, there's something humbling in all of this. That even in our most connected age, with networks that span continents and satellites that loop the globe, so much of our modern life depends on the steady behaviour of a star 150 million kilometres away. We forget sometimes that we live inside the sun's atmosphere. The solar wind never stops flowing. The magnetic field of Earth is not a fortress, but a filter, one that can be shaken, bent, and overwhelmed if the solar weather turns severe, and yet the sky does not threaten us every day. Most solar storms are mild. Most flares flare quietly. Most days the sun simply shines. But when it breathes out with anger, we feel it. Not as heat, not as light, but as silence. When screens go dark, when signals vanish, when the pulse of our machines flickers. So tonight, as you sleep beneath the sky, remember that you live not beneath a ceiling, but within a tide of particles, of magnetism, of ancient light. The sun has moods, but we have understanding, and slowly, gently, that may be enough to keep us safe. If you could peel away the surface of the Earth, dig far deeper than any mine has ever reached, pass through the stone and the pressure and the heat, eventually you would come to a sea of molten metal, a churning, roiling ocean of iron and nickel surrounding a solid core. It is from this restless heart that Earth's magnetic field is born. Invisible, ancient, and mostly forgotten in daily life, it is one of the most important forces standing between us and the deep electric breath of space. We cannot see it, but we are wrapped in it, a protective cocoon extending tens of thousands of kilometers into space, deflecting charged particles from the sun, shielding our atmosphere from erosion, and quietly preserving the conditions that make life possible. Without it, Earth might have ended up like Mars, stripped of its air, its water slowly stolen by the solar wind, its surface exposed to constant radiation. The magnetic field is generated by what scientists call the geodynamo, the motion of molten iron in the outer core stirred by Earth's rotation and the lingering heat of formation. This movement of conductive material produces electric currents, which in turn create a magnetic field. It is not fixed like a bar magnet. It is dynamic, always shifting, drifting, and over long stretches of time reversing. That's right. Earth's magnetic field has flipped many times in the past. North becomes south. South becomes north. It doesn't happen suddenly, and it doesn't happen on a schedule. The process of reversal can take thousands of years. During that time, the field weakens, becomes more complex, with multiple magnetic poles appearing in strange places before finally settling into a new configuration. The last full reversal, known as the Brunnes-Matuyama reversal, occurred about 780,000 years ago. There's evidence of shorter partial reversals since then, and some scientists believe we may be entering another period of magnetic instability. The magnetic North Pole, once reliably located in the Canadian Arctic, has been wandering at increasing speeds, now drifting towards Siberia at over 50 kilometers per year. What would happen if the field flipped again? It's difficult to say. Magnetic reversals are recorded in the geological record, etched into ancient lava flows that preserve the direction of the field as they cool. These tell us that reversals have happened many times, perhaps hundreds, over Earth's history, and life has survived every one. But that doesn't mean the process is without effects. During a reversal, the magnetic field weakens significantly, possibly by as much as 90%. This weakening allows more cosmic and solar radiation to reach the atmosphere and surface. Satellites and space stations would be more vulnerable to damage. Animals that navigate using the magnetic field, such as birds, whales, and turtles, could become disoriented. High-altitude flights might experience increased radiation levels. Power grids and communication systems, already sensitive to solar activity, would become more exposed. Some worry that ozone depletion could occur in a weakened field, leading to changes in climate or biological stress. Others caution that while these effects are possible, they're unlikely to be catastrophic. More like a long, slow pressure rather than a sudden disaster. And it's worth remembering that a full reversal is not expected overnight. These processes unfold over millennia, giving life and human technology time to adapt. Still, the idea unsettles us. We like our compass needles to point north. We like to imagine the Earth as a stable sphere, unchanging at its core. But the truth is more complex, more alive. The planet is not a static rock. It is a moving, breathing system with forces beneath our feet as dynamic as the stars above. And that invisible shield, our magnetic field, is not a wall, but a wave. It flows, it shifts, it hums with energy we can't feel but have always depended on. The next time you watch an aurora, those glowing curtains of green and pink light that ripple across the sky, you're witnessing the edge of that field, a place where the sun's particles crash into our upper atmosphere, guided by magnetic lines that reach down like invisible fingers. It is beautiful, but it is also a reminder of the vast electric weather we live within. We are lucky, in a way. Other planets lack such protection. Mars once had a magnetic field, but when its core cooled and the field faded, its atmosphere thinned and its water escaped. Venus never had a strong field at all, and now its surface bakes beneath thick, crushing clouds. Earth for now still holds on to its shield, but it may not always look the same. It may drift, wrinkle, weaken, and reverse, and when it does, we will adjust. We will shield our satellites, recalibrate our navigation, learn to live with a sky that behaves a little differently. It won't be the end. Just another change in the long story of a living planet. And perhaps, on some quiet night far in the future, a navigator will stand on the deck of a ship, compass spinning oddly in hand, and smile. Because they'll know. The Earth is not broken, it is simply changing its mind. So sleep well. Beneath the invisible shield that holds the sky at bay, it may shift, it may flicker, but for now it holds, and that is enough. If you could stand on the surface of Io, Jupiter's most restless moon, you wouldn't stand for long. Beneath your feet, the ground would quake, rise, and sometimes burst open. Fountains of molten sulfur might erupt nearby, colouring the sky with clouds of orange, yellow, and red. The land would shimmer with heat, not from a sun above, but from the tormented heart of the world itself. And above you, hanging impossibly large in the sky, Jupiter would loom, a striped, swirling titan watching over a moon that never knows stillness. Io is not a place of silence. It is a place of pressure and release, a celestial pressure cooker where geology refuses to sleep. At first glance, it seems impossible that a small moon, slightly larger than Earth's own, could be so violent. But the answer lies in the push and pull of giants. Io is caught in a gravitational tug-of-war between Jupiter and its fellow Galilean moons Europa and Ganymede. As Io orbits, it doesn't follow a perfect circle. It stretches, it compresses. This constant tidal flexing generates heat, not from the outside, but from within. This process, called tidal heating, is the same mechanism that warms Europa and Enceladus, though with different results. On Io, the energy manifests as volcanoes, more than 400 of them, some erupting with plumes that shoot hundreds of kilometres into space. The heat is so intense that Io is the most volcanically active body in the solar system. Its surface is a patchwork of colour, bright yellows from sulphur deposits, reds and blacks from molten lava, and greys where older eruptions have cooled. There are no craters. Any impact marks are quickly buried or erased by the moon's own geology. The landscape is constantly being rewritten. We first glimpsed this violent world during the Voyager missions in 1979. Until then, astronomers assumed Io would be a quiet, cratered satellite, similar to our moon. But Voyager 1 revealed something astonishing. A plume erupting from the surface, captured by the spacecraft's camera just in time. It was a moment of revelation, proof that volcanic activity wasn't unique to Earth. Since then, other missions, Galileo, Juno, and various telescopic studies, have given us a more detailed picture. We've seen lava lakes, some the size of entire cities, constantly churning. We've observed eruptions bright enough to be seen from Earth-based observatories. And we've learned that Io's atmosphere, though thin, is made largely of sulphur dioxide, a gas that sometimes freezes onto the surface at night, only to sublimate back into vapour as the sun rises. Io is a world in motion, in a way that feels almost alive. But what does it teach us? First, it shows us that planetary energy doesn't have to come from sunlight. On Earth, much of what we think of as life and activity is powered by the sun. Plants grow, oceans warm, winds blow. But on Io, the power comes from gravity, from the invisible force of orbits and resonance. That energy, invisible but constant, reshapes rock, stirs molten cores, and fuels eruptions. It also reminds us that geology is not a passive process. Many moons in the outer solar system are thought to be cold, inert spheres of ice and dust. But Io contradicts that image. Its interior is dynamic, its surface is dangerous. It challenges the notion that small means simple, or that distance from the sun means silence. And for scientists, Io is more than just a curiosity. Studying its volcanic activity helps us understand early Earth, a time when our own planet was hotter, more violent, and constantly reshaping itself. By watching Io, we can glimpse what the Earth might have been like 4 billion years ago, when continents were still forming and the air smelled of sulphur and fire. There's also something humbling about Io's relationship with Jupiter. Imagine standing there, assuming somehow you could survive the radiation and the heat. You would look up, and Jupiter would take up half the sky, not as a distant point of light, but as a vast banded world, its storms and stripes visible in breathtaking detail. And you would feel, in that moment, what it means to be small, to live not beneath a sky, but beneath a planet. This relationship is not poetic metaphor. It is physical reality. Jupiter's immense gravity shapes Io's orbit, creates its tides, and through those tides generates the very heat that drives its volcanoes. In a way, Jupiter is both parent and tormentor, the source of both power and pain, and so Io continues to burn. It is not hospitable. It does not whisper of hidden life or gentle warmth. but it belongs in our story because it shows that planets and moons are not static balls of rock. They breathe, they bleed, they evolve. And in their fiery landscapes we see echoes of the forces that once shaped our world and that still simmer beneath our own feet. Io reminds us that sometimes the most distant places are not the quietest. Some moons do not freeze in the dark, some burn, and while they burn, they teach. Far from the warmth of the sun, in the shadowed outskirts of the solar system, there are moons that should be frozen solid. By every expectation, they ought to be still, lifeless and silent, locked in the cold embrace of ice and time. But they are not. Beneath their frozen surfaces, something stirs, something flows. Europa and Enceladus, moons of Jupiter and Saturn respectively, defy the narrative of distance and desolation. They offer a quiet whisper of warmth in the cold, a hint that even in places where the sunlight cannot reach, life might still find a way. Let us begin with Europa. Europa is a smooth world, strikingly so. Its surface is crisscrossed by long dark lines, fractures that cut across an otherwise bright icy crust. It has remarkably few impact craters, suggesting that the surface is relatively young and constantly renewing itself. But it's what lies beneath the surface that has captivated scientists for decades. Under that cracked shell of ice, estimated to be between 10 and 30 kilometers thick, is believed to be a vast global ocean. Liquid water kept from freezing not by the distant sun, but by the same mechanism that fuels Io's volcanoes, tidal heating. As Europa orbits Jupiter, the gas giant's gravity stretches and compresses it slightly with every pass. This subtle but constant flexing generates heat inside the moon, enough to maintain an ocean beneath the ice, and not just a pond or a reservoir. Models suggest that Europa's subsurface ocean could contain more than twice the volume of all Earth's oceans combined. An ocean, deep, dark, and hidden, shielded from radiation, stable over geological time, and perhaps in contact with the rocky mantle below. That last detail is especially important, because on Earth, life thrives in places where water meets rock, particularly around hydrothermal vents at the bottom of the ocean, where volcanic heat provides energy in the absence of sunlight. Could something similar be happening on Europa? We don't know yet. But there are tantalizing clues. In 2012, and again in later years, the Hubble Space Telescope detected signs of water plumes erupting from Europa's surface, geysers of liquid water blasting through cracks in the ice and venting into space. If confirmed, these plumes would offer a way to sample the subsurface ocean without drilling through kilometers of ice. It's like the moon is exhaling, offering hints of what lies beneath. Then there is Enceladus. Smaller than Europa, and orbiting Saturn instead of Jupiter, Enceladus was once thought to be an unremarkable, icy rock. But that changed dramatically in 2005, when the Cassini spacecraft flew by and observed enormous plumes erupting from the moon's south pole. Not once, but repeatedly. These plumes were not just steam. They contained water vapor, salts, silica, and organic molecules, the building blocks of life. Further analysis showed that these jets were originating from a subsurface ocean beneath the ice. Tiny grains of icy material, laced with complex chemicals, were spewing out through fractures known as tiger stripes, long warm cracks that run across the southern hemisphere. Cassini even flew through the plumes, sampling the spray directly and confirming that Enceladus has liquid water and organic chemistry. What makes both Europa and Enceladus so fascinating and so emotionally resonant is not just the possibility of life. It's the idea that life might exist in a place so far removed from everything we've ever known. These moons are not bathed in light. They do not have forests or clouds or birdsong. They have no sunlight streaming through blue skies, and yet beneath layers of ice, warmed by tidal forces and stirred by geology, there might be oceans teeming with microbial life. It is not a guarantee. The conditions are right, but life is not inevitable. Still, the ingredients are there: water, heat, chemistry, and time. What might that life look like? If it exists, it is likely microbial, clustered around undersea vents, feeding on minerals or chemical gradients. It may be nothing more than simple cells, or it may be something stranger, adapted to conditions we can barely imagine. Life that evolved in total darkness, with no need for photosynthesis or atmospheric oxygen. Life that never saw the stars. And yet, in that darkness, it would still be life. Both NASA and the European Space Agency are planning missions to explore these possibilities further. NASA's Europa Clipper, launching in the mid-2020s, will orbit Jupiter and perform dozens of close flybys of Europa, mapping its surface, analysing its composition, and searching for signs of habitability. Meanwhile, ESA's JUICE mission, the Jupiter Icy Moons Explorer, will study Europa, Ganymede, and Callisto, focusing on their potential as ocean worlds. Enceladus, too, may one day be revisited. Proposed missions could carry instruments capable of flying through the plumes again, this time with even more sensitive detectors, looking for biosignatures, the subtle fingerprints of living processes. But even before those missions arrive, Europa and Enceladus have already changed the way we think about habitability. They've shown us that the habitable zone, the Goldilocks region around a star where liquid water can exist, is not the only measure that matters. Life may not need sunshine, it may only need warmth, water, and time. And if that is true, then life might be far more common in the universe than we once believed. Not on desert planets with blue skies, but in the dark, beneath miles of ice. So tonight, as you rest, think of these moons, not as cold rocks circling faraway giants, but as cradles. Cold cradles with warm hearts. Oceans hidden in the dark. Silence above, movement below. And maybe, in the deepest blackness, something stirring. Slowly, gently, alive. If you were to float down through Titan's thick atmosphere, you might feel, briefly, as though you were falling through an Earth-like dream. There are clouds, there are rivers, there are lakes and even seas. The landscape below is sculpted by erosion, with winding channels carved by flowing liquid and deltas where that liquid empties into broader basins. But it would not take long to realise that this is not Earth. The rivers are not water, but methane. The lakes are not blue, but black. The ground is covered in organic dust, and the air, though rich and dense, is too cold to breathe. Titan is a world where everything familiar has been rewritten in the language of deep, cold and exotic chemistry. It is Saturn's largest moon, even larger than Mercury, and in many ways it is one of the most Earth-like places in the solar system, not in terms of temperature or biology, but in terms of complexity. It has weather, it has geology, it has cycles, clouds form, rain falls, rivers run, and lakes collect. It is the only place beyond Earth known to have stable liquid on its surface. But here, the liquids are hydrocarbons. At Titan's surface temperature, around minus 180 degrees Celsius, water is as hard as rock. It forms the bedrock and mountains, immovable and ancient. Meanwhile, methane and ethane, gases on Earth, exist as liquids, flowing across the land and collecting in vast lakes, especially near the poles. These lakes can be hundreds of kilometres across, with wave patterns and changing shorelines. Some are tranquil, others windswept. There are even suggestions of seasonal rainstorms, as Titan's atmosphere shifts with its orbit around Saturn. That atmosphere too is a wonder. It is thick, denser than Earth's, and made mostly of nitrogen, with a smattering of methane and complex organic compounds. This density means a human could, in theory, fly through Titan's skies with nothing more than flapping wings and a good pair of lungs, if not for the cold and the toxicity. But from a spacecraft's point of view, Titan's sky glows with a golden haze. Sunlight filters through slowly, scattering into a perpetual twilight. In 2005, the European Space Agency's Huygens probe landed on Titan. It was the first and only landing ever accomplished in the outer solar system. As it descended through the clouds, it photographed a landscape of ridges and valleys, of branching channels and dark plains. It saw rounded pebbles on the ground, likely made of water ice smoothed by methane rivers, and it recorded a panorama of a world that felt, despite everything, strangely familiar. Since then, the Cassini spacecraft orbited Saturn for more than a decade, flying past Titan again and again, using radar to peer through the haze and map the surface. It discovered dunes the size of skyscrapers, long lines of wind-blown organic material that stretch for hundreds of kilometers. It revealed empty lake beds, changing shorelines, and perhaps even signs of cryovolcanoes, icy mountains that may erupt with slush and ammonia, reshaping the landscape in slow, frigid motion. Titan is dynamic. It is not a frozen fossil. It breathes in its own way. But the question that stirs most curiosity is this: could there be life? Not life as we know it, not water-based, not built on oxygen, but something stranger, something methane-based. On Earth, all known life depends on liquid water as a solvent. But some scientists wonder whether methane could serve a similar role. It's less polar, less able to dissolve many substances, but at Titan's temperatures, it may be stable enough to support complex chemistry. There's even a name for hypothetical life forms that might evolve in such conditions: azotosomes, membranes made from nitrogen-rich molecules that could function like cell walls in a methane medium. No such life has been found, of course, but Titan reminds us that our definition of habitability might be too narrow. That Earth is one story, but not necessarily the only one. In 2027, NASA plans to launch a mission called Dragonfly, a rotorcraft that will fly across Titan's surface, landing at different sites to study its chemistry and geology. It will search for complex organics, for evidence of prebiotic chemistry, and perhaps, just perhaps, for signs that Titan's alien rivers have shaped more than just land. Even if no life is found, Titan is still extraordinary. It offers a glimpse into a world where chemistry follows different rules, where rivers are cold and black, where mountains are made of frozen water, where it rains liquid gas, and in a way, it also shows us ourselves. Because the molecules that rain from Titan's skies, tholins, complex organics formed by sunlight and methane, are the same building blocks that may have rained on early Earth. Before life began here, our own planet may have worn a similar orange haze, rich in prebiotic chemistry. Titan could be a snapshot of our own past, a slow-motion prelude to life, frozen in amber. Or perhaps it's a path not taken, a different kind of world, following different rules, dreaming different dreams beneath its methane clouds. There is poetry in that, in the idea that rivers can run without water, that skies can glow without sunlight, that life, or something close to it, might rise in silence, far from the warmth of a star. So tonight, as you drift towards sleep, think of Titan, a moon where lakes are black, where the air is thick, and where alien chemistry flows in steady, patient rhythms. It is not Earth. It is not like Earth. And yet, in its strangeness, it tells us something profound, that the universe is not limited to our story, and that other stories may be waiting just beyond the clouds. There is a quiet paradox in the story of volcanoes. They are, by reputation, destroyers, sudden and violent, swallowing forests, burying cities, darkening skies. They roar from beneath the earth, reshaping land in moments and altering climates for years. But they are also something else, something gentler. They are builders, givers, life-bearers. For in the same breath that they end, they also begin. In their heat, chemistry is stirred. In their ash, soil is enriched. In their plumes and vents, the building blocks of life are released. Volcanoes may end chapters, but they also write prologues. And this duality isn't confined to Earth. Across the solar system, volcanoes appear again and again. Not always spewing fire, not always towering in cones, but always marking places where energy moves and matter transforms. They remind us that a world need not be warm on the surface to be alive inside. That motion deep below can create possibility above. On our own planet, volcanoes have shaped continents. They've built islands from the sea floor. They've carved valleys, released greenhouse gases that warmed the early Earth and brought minerals to the surface that would later nourish life. The air you breathe, rich in oxygen now, was once thick with volcanic gases. And though too much volcanism can choke and bury, too little can leave a planet stagnant, its atmosphere thin, its surface sterile. In the ancient past, when the Earth was young, its crust had barely formed. The planet's surface was a hellscape. Oceans of lava, a sky of toxic gases and a constant rain of space debris. And yet, even then, volcanoes were working. They vented carbon dioxide, creating the greenhouse effect that eventually stabilized Earth's temperature. They spewed water vapor, much of which condensed and became the oceans, and around undersea vents, far from the sun's reach, life may have begun. These hydrothermal vents, still found in the deep oceans today, are cracks in the seafloor where seawater meets magma. The heat causes chemical reactions, releasing hydrogen, sulfur compounds and metals, all of which form the basis of thriving ecosystems. Whole communities of organisms, clams, tube worms, shrimp, live in complete darkness, feeding not on sunlight, but on chemistry. Some scientists believe it was here, in these volcanic cradles, that the first cells formed. And so, the idea that volcanoes are merely catastrophic overlooks this deeper truth, that fire can nurture, even as it destroys. We see this beyond Earth as well. On Io, the relentless volcanism reshapes the moon daily. There is no water, no life, not that we know, but there is activity. There is change. It is a world that teaches us what happens when tidal heating goes unchecked. Europa and Enceladus, though quieter above, may be volcanically active below, not with magma, but with water. Cryovolcanoes on these moons could erupt slush and salt water, cycling nutrients and heat within the hidden oceans. This kind of underwater volcanism is exactly what could make those oceans habitable. Not warm in a tropical sense, but warm enough to allow chemistry, circulation, and perhaps even biology. Even Mars, now seemingly dead, bears scars of a volcanic past. Olympus Mons, the tallest mountain in the solar system, is a volcano, and a testament to what can grow when tectonics are calm and eruptions build endlessly upward. Some believe Mars may have once been volcanically active enough to support a thicker atmosphere, even liquid water. On Venus, the story is different again. There, volcanism may be ongoing, hidden beneath clouds of sulfuric acid. Radar images from orbit show shifting features, new flows, changing patterns. If true, it suggests that even our planetary twin, hostile as it is, still moves and breathes beneath its shroud. Everywhere we look, volcanoes blur the line between dead and alive, because volcanism isn't just about molten rock, it's about energy flow, the transmission of heat from a world's interior to its surface. And where there is flow, there is potential. Movement means cycles. Cycles mean complexity, and complexity eventually can mean life. But volcanoes are also reminders of fragility. The same eruptions that created fertile soil can also bring famine. In 1815, Mount Tambora exploded in Indonesia. The blast was so powerful that it ejected ash into the stratosphere, reducing global temperatures and causing what became known as the year without a summer. Crops failed across Europe and North America, Skies turned grey, and thousands died, not from the eruption itself, but from the cascade of consequences. There's a lesson in that too. Volcanoes do not care. They are not villains, nor are they guardians. They are simply the planet speaking, sometimes in whispers of steam, sometimes in roars of fire. They are how worlds express their inner lives, and in that expression they reveal something profound. That life, even on Earth, is not cradled in serenity. It is cradled in motion, in instability, in places where extremes meet. Hot vents in cold oceans, rich soil on barren slopes, ash clouds that dim the sun and later bring rain. If life exists beyond Earth, it may not emerge in a calm meadow beneath blue skies. It may begin beneath ice, near heat, in the deep and in the dark. It may need fire to begin. And so, as you drift tonight, consider that the same volcanoes we fear, the ones we watch with nervous eyes and study with cautious minds, may be the very reason we are here. Not just because they made the land we walk on, or the air we breathe, but because they created places where chaos and chemistry could mingle, long before memory, long before light. And maybe, on a distant moon beneath a crust of ice, another volcano is doing the same, writing the first words of another story, in heat and in silence. From the outside, Earth appears ordinary. A pale blue marble in the vast dark sea circling an average star in an unremarkable corner of the galaxy. And yet, behind this appearance of normalcy lies a story stitched together by extraordinary chances. A chain of coincidences, balances, collisions and alignments, none of them guaranteed, all of them essential. We're here not because the universe required it, but because, against all odds, this particular planet survived. It begins, as many cosmic stories do, in a cloud of dust. Roughly 4.6 billion years ago, a dense region of gas and dust in the Milky Way began to collapse under its own gravity. Most of the material formed the Sun, igniting nuclear fusion and flooding the newborn solar system with light. The rest, a swirling disk of debris, slowly gathered itself into clumps. These clumps collided, stuck together, shattered, reformed, and grew. Some became gas giants. Others stayed small and rocky. Among them, in the inner solar system, Earth began to take shape. But Earth, as we know it, didn't emerge from the dust fully formed. It was moulded by chaos, by heat, by bombardment, by violence. In its infancy, Earth was struck by another protoplanet, a body roughly the size of Mars. The collision was catastrophic. Both objects partially melted. A cloud of molten debris circled Earth and, over time, coalesced into the Moon. This might seem like destruction, but it was also creation. The Moon, large relative to Earth, plays a critical role in stabilizing our planet's axial tilt. That stability regulates the seasons, preventing extreme swings in climate. Without the Moon, Earth might wobble wildly, swinging from ice ages to fiery droughts in unpredictable cycles. It's a silent guardian, not just beautiful in the night sky, but essential to the long-term habitability of our world. Then there was water. Our planet didn't begin with oceans. Its early surface was molten, its skies toxic. But during the period known as the Late Heavy Bombardment, when leftover debris from the solar system's formation rained down in waves, icy comets and water-rich asteroids collided with Earth. They delivered water, not in buckets, but in billions of tiny impacts, enough eventually to flood the basins, fill the clouds, and create the seas. Another piece fell into place, and yet, water alone is not enough. A planet also needs protection, not from meteors, which can be seen, but from invisible particles, radiation, solar wind, cosmic rays. Here too, Earth got lucky. Unlike Mars, Earth is large enough and hot enough inside to keep its iron core partially molten, That molten core rotates and convects, generating a magnetic field that envelops the planet in a protective bubble. This magnetic field deflects charged particles from the sun, preserving the atmosphere, preventing it from being stripped away. Without it, the air would thin, the oceans might evaporate, and the surface would bake in ultraviolet light. Even our position in the solar system seems unusually fortuitous. Not too close to the sun, where oceans would boil and carbon dioxide would dominate the skies. Not too far, where water would freeze and sunlight would fade. But just within that narrow band where liquid water can persist. The so-called habitable zone. A place where warmth is balanced by distance, and light falls gently rather than harshly. And then there are the gas giants, especially Jupiter. Its immense gravity acts like a cosmic vacuum cleaner, sweeping up many comets and asteroids that might otherwise threaten the inner planets. It doesn't catch them all, but it catches enough. In simulations of solar systems without a Jupiter-like planet, bombardments are more frequent and more devastating. So even the distant, stormy world we see through telescopes plays a quiet role in Earth's stability. All of these factors, the moon, the oceans, the magnetic field, the position, the shielding from Jupiter, could have gone another way. They almost did. And on countless other worlds and countless other systems, they probably did. That's why scientists sometimes speak of Earth not as inevitable, but as improbable. Not the rule, but the exception. A rare alignment of accidents that happened, this one time, to produce a world where chemistry became complexity, where molecules folded into proteins, and proteins danced into cells, and cells multiplied into forests, birds, thoughts, and dreams. And so, when we look up at the stars and wonder why we haven't heard from anyone else, when we contemplate the silence of the cosmos, perhaps it's not because life is rare, but because survival is. Perhaps many worlds began the journey, but few made it through the gauntlet of radiation, instability, bombardment, and loss. Perhaps Earth passed through filters that crushed others, not because we are chosen, but because we are lucky. That's a different kind of beauty, a different kind of meaning. We're not guaranteed, we're not permanent, but we are here, and that, tonight, might be enough to marvel at. You're breathing air held close by a magnetic field, standing on land formed by collisions, drinking water brought by wandering ice. You're orbiting quietly in a zone of chance, lit by a star that has not yet flared too wildly. A star that, for now, simply shines. Once, Mars may have been blue. Not entirely and not for long, but long enough to matter. Its surface holds traces, dry riverbeds, ancient deltas, minerals that only form in water. Satellite images reveal winding canyons carved not by wind but by flowing streams. There are signs of lakes that filled and drained, of shorelines etched into stone. And scattered across its surface lie the ghost imprints of rainfall, of weather systems that, for a time, may have made the planet feel not entirely unlike Earth. But that was long ago. The Mars we know now is silent, dusty, and dry. Its skies are thin and orange, its winds sharp but weak. The rivers are frozen in memory. The lakes are buried under layers of rock and frost, and the warmth that once ran through its surface has all but vanished. Mars is more than a neighbour. It is a cautionary tale. It is often described as Earth's little sibling. Smaller, lighter, a planet that started with many of the same ingredients, but followed a very different path. And that divergence wasn't caused by a single catastrophe. It happened slowly, gradually, a quiet fading, one mechanism at a time. To begin with, Mars is only about half the diameter of Earth. That smaller size meant it lost heat faster. Its core, once molten and active, began to cool, and with that cooling came a crucial loss, the magnetic field. Just like Earth, Mars likely had a magnetic field early in its history, generated by the movement of molten iron in its core. That field would have protected the atmosphere, deflecting solar, radiation, and keeping the planet's air thick enough to trap heat and allow liquid water to flow. But without the internal motion to sustain it, the Martian dynamo shut down, the magnetic field collapsed, and the solar wind, that steady stream of charged particles from the sun, began to strip the atmosphere away. It wasn't a sudden event. It didn't happen in days or weeks, but over millions of years, molecule by molecule, Mars lost its air. Without a thick atmosphere, surface pressure dropped. Without pressure, liquid water could no longer remain stable. It evaporated into space or froze beneath the surface. Temperatures fell, weather patterns collapsed. Life, if it had begun, would have found survival nearly impossible. Today, the Martian atmosphere is less than 1% the thickness of Earth's. It's made mostly of carbon dioxide. It can't support liquid water on the surface. Even the warmer summer days in the equatorial regions rarely allow ice to melt, and even then only for moments. The planet is now a desert, not of sand but of history, a place where something promising once existed, and then didn't. Rovers like Curiosity and Perseverance still explore the landscape. They search for signs of ancient microbes, for chemical clues in the rocks, for the fingerprints of water long gone. Orbiters circle above, mapping ice caps and dust storms, taking measurements that tell a story not of extinction, but of potential cut short. And we are drawn to that story, because when we look at Mars, we see a version of what could have been, a twin that didn't make it, a reminder that planets are not guaranteed permanence, that habitability isn't a switch flipped once and forever, but a balance, one that can shift with cooling cores, weakening fields, or changing skies. Some scientists even speculate that Earth could, in time, face similar fates. Not in years or even millennia, but in the slow turning of eons. If Earth's core were to stop churning, our magnetic field would eventually weaken. Solar wind could begin eroding the upper atmosphere. Climate systems could shift. The biosphere would adapt, at first, but the trajectory would be familiar. Of course, Earth is larger, our core is still hot, our field is still strong. But Mars shows what can happen when those systems falter. It also shows how easily things can go quiet. We often talk about terraforming Mars, the idea that we might one day warm it, thicken its atmosphere, release the ancient water trapped beneath the ground, that we might turn the red world green. It's a dream rooted in hope, but also in irony, because Mars was in some ways already terraformed once, by nature, by time, by accident, and then it lost it. Terraforming it again would not be creating a miracle, but restoring a memory, and in that perhaps is the deepest lesson. Worlds are not static, they are stories. They rise, they change, they cool, they sleep. Mars is not a failure, it is a chapter. One that speaks softly across space and time to anyone willing to listen. A chapter that warns us that planets are delicate, that habitability is not a permanent feature but a temporary gift, that Earth too must be watched, tended and respected, not because it will vanish tomorrow, but because it doesn't owe us anything. The conditions that allow us to exist are not fixed. They are earned in geological time, and held only so long as the balance is maintained. So tonight, as you look toward the sky, find Mars, a red pinprick of light, calm in the darkness. Remember that it was once warm, once wet, once kissed by clouds and touched by rain, and now it is quiet. And know that Earth still turns, still breathes, still holds the warmth of life, but nothing lasts without care. Some dangers come with flashing lights and loud alarms. We see them forming in the distance, measure them, give them names, build models to predict their paths. We feel safe when we can point to a chart or a telescope image and say, there it is. But the universe is not required to show us all its cards. Some things don't come with warnings. Some things don't even make sense until long after they've passed. And some, the most profound, may never give us the courtesy of recognition at all. We call them the unknowns, not because they are mysteries waiting to be solved, but because they are questions we may not yet know how to ask. Among the possibilities that drift quietly through scientific theory are events that sound more like fiction than fact, and yet they arise not from speculation, but from the logical consequences of physics as we currently understand it. One such possibility is known as false vacuum decay. It begins with a deceptively simple idea that the universe we live in may not be in its most stable configuration. We assume that the fabric of reality, the vacuum of space itself, is in a state of lowest possible energy. But if it isn't, if we occupy what physicists call a metastable vacuum, then there's a possibility, however remote, that a more stable state exists. And if some region of the universe ever tips into that lower state, it would create a bubble of true vacuum that expands at nearly the speed of light, rewriting the laws of physics as it moves. It would be unstoppable, undetectable in advance. No warning, just gone. Of course, this is theoretical. And the good news, if one can use such a phrase, is that if such an event ever occurred, we would never know, not even for a moment. Then there is dark energy, the unseen force that causes the universe's expansion to accelerate. We don't know what it is. We don't know why it behaves the way it does. We only know it's out there, embedded in the equations that describe the movement of galaxies. It makes up roughly 68% of everything, and we barely understand it. What if it isn't constant? What if it shifts? A small change in its nature could have enormous consequences. Not in seconds, perhaps, but over millions of years, tipping the universe toward collapse, or stretching it so thin that stars no longer form. Again, there is no indication that this will happen, but the possibility reminds us how much we do not grasp. Even more quietly, there are the interstellar clouds, vast cold regions of gas and dust that drift between the stars. If our solar system were to pass through a dense one, and there is evidence it has before, it could have subtle but widespread effects. The pressure from surrounding gas could compress the heliosphere, allowing more cosmic radiation into the inner solar system. That increase in radiation could affect planetary climates, perhaps even strip atmospheres over time. Unlike an asteroid impact or a solar flare, these clouds are not dramatic. They move slowly, silently, reshaping conditions not in moments, but in centuries. A whisper rather than a scream. There are other possibilities too. Variations in fundamental constants, phase transitions in exotic matter, or even topological defects left over from the early universe. These terms live mostly in the domain of theoretical physics. They are shadows we glimpse from the corner of our understanding, not monsters but silhouettes, not prophecies but questions. And perhaps the deepest unknown of all is this. We don't know how much we don't know. It's tempting to believe that our telescopes have shown us everything, that our equations describe the world in full. But every advance in science has revealed another layer beneath the one we thought was final. There are likely phenomena we haven't imagined, particles we haven't detected, forces we haven't named. Some may be harmless curiosities, others may be woven into the fates of worlds. This is not meant to frighten you, quite the opposite. There is a kind of peace in recognizing that not everything rests on our shoulders, that the universe is vast and old and does not hinge on our awareness. If some silent shift were to arrive from beyond the edge of understanding, it would do so not out of malice, but as part of a dance far larger than us. We are not the choreographers of reality, only brief dancers, moving softly across the stage for a time. And yet, for all the unknowns, there is still something deeply comforting. The stars are still there. The earth still turns. The oceans still rise and fall with the moon's pull. Life, improbable as it is, continues. We don't need to solve every mystery to exist meaningfully. Sometimes it is enough to simply recognize the mystery and be still with it. So when we speak of threats we haven't discovered, we're really speaking of humility. A humility that says, we are small, but we are aware. We don't know everything, but we are learning. We don't control the cosmos, but we walk through it with open eyes. And maybe that is all the universe ever asked of us. When you look up at the night sky, the stars seem countless. Thousands visible to the naked eye, billions in our galaxy, and likely trillions more galaxies beyond that. The sheer number suggests something almost inevitable. If Earth could produce life, surely other planets could too. And if life could evolve into intelligence here, surely somewhere else it has as well. But then comes the silence. No signals, no landings, no vast galactic community welcoming us. Just stars, burning quietly, refusing to answer. This, in essence, is the Fermi paradox. Named after physicist Enrico Fermi, the paradox asks a simple question. Where is everyone? If the universe is so big and so old and the conditions for life seem common, why haven't we seen evidence of others? Why haven't we heard a whisper from the stars, a flicker of artificial light, a message travelling across the void? One possible answer is known as the Great Filter. It's a hypothesis that somewhere between the birth of life and the rise of intelligent civilizations capable of spacefaring contact, there is a step, a barrier, that is nearly impossible to cross, something that stops most, if not all, civilizations from surviving long enough to make themselves known. And no one knows where this filter is. It could be behind us. Maybe the leap from chemistry to biology is incredibly rare. Maybe the transition from single-celled life to multicellular organisms is even harder. Or perhaps intelligent life usually evolves, but lacks the stability, culturally, environmentally, or technologically to last. If the filter is behind us, we are rare, unbelievably rare, perhaps even unique. And the silence isn't threatening. It's peaceful. We made it through. We're the lucky ones. But the darker possibility, the one that lingers at the edge of thought, is that the filter lies ahead. That civilizations tend to rise, build, explore, and then collapse. That there comes a point where intelligence creates its own end, through war, environmental failure, artificial intelligence, or some unknown catastrophe we have not yet encountered. And if that's true, then the reason we haven't seen others is not because no one else existed, but because no one else lasted. It's a quiet thought, not a scream, not a prophecy, just a whisper. Maybe intelligence isn't the solution to survival. Maybe it's the test. Of course, all of this remains speculative. We don't know how life started on Earth. We don't know how often it starts elsewhere. We don't know what kinds of dangers civilizations face once they build technology, nor how often they find ways through those dangers. But what makes the Great Filter so powerful is not that it's terrifying, it's that it's humbling. It reframes the silence of space not as a mystery to solve, but as a reminder to listen. It tells us that our existence is not guaranteed, that our survival is not automatic, and that the moment we inhabit, right now, may be far more delicate than it seems. We are in a sliver of time where we can look out, wonder, send probes and record histories. We can reflect on our past, imagine futures, and ask who else might be doing the same. But we are not beyond danger. We are not past the filter. Not yet. And so, what does this mean for us? It means that everything we do matters. That every act of preservation, of our environment, of our knowledge, of our curiosity, is an act of survival. That every effort to understand the cosmos and to protect the Earth is a way of leaning against the filter, of pushing just a little further, of hoping that the silence isn't final. It also means that maybe, just maybe, we are the first, that no one else has made it through, that the universe is waiting for a voice to rise above the quiet, and maybe that voice could be ours. Or perhaps others have survived, but long ago. Perhaps they watched their skies, saw silence too, and grew into civilizations so different, so advanced, or so subtle, that their presence leaves no footprint we know how to see. Perhaps the signs are there, woven into gravitational waves or neutrino streams, and we simply haven't learned how to read them yet. In either case, the message is the same: we do not know, but we are here. We are perched on a narrow ridge, between the known and the unknown, the visible and the invisible. We are the product of accidents and balances, of collisions and chemistry, of luck and resilience. And whether the great filter is behind us or ahead, we have this moment, this breath, this sky, this chance to look outward and inward at the same time. And maybe that is enough. Maybe the purpose of knowing the risks isn't to panic, but to appreciate, to see clearly and still choose to build, to feel small and still speak, to know the odds and still reach. So tonight, as the stars settle over you, let the silence be not a threat, but an invitation to wonder, to continue, to listen, and maybe, just maybe, to be the first voice that answers back. Imagine for a moment the night sky above you, not the scattered constellations traced in childhood books, nor the familiar arc of the moon's pale face, but the full breadth of it, the quiet tapestry, the gentle speckle of light across a darkness so deep it hums. It looks still, it looks eternal, and yet, as we've journeyed together tonight, you've seen what few ever truly pause to consider, that stillness is an illusion. The stars above us flare and burn, collapse and explode. Invisible winds flow through galaxies. Energies rise and fall across incomprehensible scales. There are storms on suns, jets from black holes, collisions between stars, and events that don't make sound because space has no air, but would make thunder in your thoughts if you could feel their magnitude. And still, here you are, not destroyed, not undone, not even anxious if we've walked this path gently enough together, just here, breathing, listening, drifting into sleep. Because as large as the dangers are, so too is the quiet power of understanding them. To know something is not to become helpless before it, but to hold it lightly, like a stone warmed by the sun. There is a kind of peace in naming the stars and their fury. There is dignity in knowing what might undo us, and continuing anyway. This is not fear. This is awareness. You've wandered through the burst of gamma rays, stood beneath the fury of invisible solar storms, watched rogue planets pass by like silent phantoms. You've flown to volcanic moons and icy oceans, to red deserts that remember rivers, and to Earth itself. Lucky, improbable, spinning still. And you've returned, not with panic, but with perspective. Because woven through all of it, every black hole jet, every neutron star collision, every ripple of possibility is something else. Us. Not just as observers, but as participants. As beings who notice, who study, who reach. We don't just stare up in awe. We send probes. We build models. We look for patterns in the sky, and we write poetry when the equations fall short. We are vulnerable, but we are also vigilant. There's something extraordinary about the fact that our species, made of water, bone, stardust and time, has learned to protect itself not with claws or fangs, but with data. Satellites track asteroids. Telescopes scan for anomalies. Computers simulate futures. Scientists decipher radiation signatures in distant galaxies to understand threats that may never touch us. This too is a kind of shield, not forged of metal, but of attention. We are stargazers with shields of data. That metaphor isn't meant to be clever, it's meant to be comforting. Because behind every scientific instrument there's a person, and behind every person, a long history of others who looked up, wondered, and chose to learn rather than fear. We are the inheritors of curiosity, and that makes us more resilient than we appear. There's also beauty in the very process of watching, to see the universe for what it is, dangerous, vast, indifferent, and still find wonder, still create meaning, still whisper goodnight under stars that don't even know you're here. That's not denial, that's courage. It's the kind of courage that doesn't roar, but instead lies very still and continues breathing. We often think of survival as brute strength or cleverness, but perhaps survival, real, long-term survival, begins in a quieter place, in awareness, in attention, in the decision to observe, prepare, and still, somehow, fall asleep peacefully at the end of the day. Because after everything we've explored, the sky hasn't changed. The stars are still where you left them. The earth is still turning. Your heartbeat is steady. The dangers we've described haven't vanished, but they haven't arrived either, and most never will. So you are allowed to rest. You are allowed to lie back and let the slow music of the cosmos play in the background, knowing you are part of it. Fragile, yes, but luminous in your own quiet way. Some people hear about the vastness of space and feel small. Others, like you, hear about its silence, its fury, its patience, and feel not small but placed. Perfectly, improbably, placed in a universe that does not need you, but still contains you. That offers no guarantees, but still lets you look up. And if that is not a kind of grace, I don't know what is. Tonight, you sleep not in ignorance of danger, but in full awareness of it. And still, you sleep. That is a triumph, a soft, unnoticed one, but a triumph nonetheless, because it means you've walked through the storm of knowing and emerged with wonder intact. And so, rest now. Not because everything is safe, but because you understand that not everything has to be. Rest, because knowledge and rest are not opposites. They are companions. Rest because the stars are still out there and you are here, still breathing, still orbiting, still watching. You are here, in this moment, breathing, listening, existing on a small spinning planet that sails through space, warmed by a single star, protected by an invisible field, and wrapped in just enough air to keep the miracle going. And that is enough. It doesn't always feel like it. The world around you hums with busyness, deadlines, alerts, questions waiting to be answered. You're asked to plan, to solve, to push forward. But for just a moment, here in the dark, in this quiet space we've made together, you're allowed to let go of all that. Because existence, in and of itself, is extraordinary. The universe is old, 13.8 billion years old. Time enough for galaxies to form and stretch, for stars to be born and die, for dust to swirl into planets and moons and rings and comets. Time enough for entire civilizations, if they exist, to rise and vanish without ever touching us. And in that long sweep of cosmic time you arrived, just now, just here. There are molecules in your body that once travelled through ancient stars. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all forged in places you'll never see, in moments that ended long before Earth was formed. You are, in the most literal way, made of stardust. But more than that, you are made of timing, of alignments, of chances that stack themselves just so, until they became breath and thought and memory. Sometimes it's easy to forget how rare it is to be conscious, to notice, to ask questions, not because you're in danger, but because you're curious. You've crossed a universe of silence and emerged as someone who can whisper, "I am here," and that whisper matters. Not because the stars need to hear it, but because you do. You've walked through vast stories tonight, gamma ray bursts, ancient impacts, solar flares and volcanic moons. You've watched Mars fall quiet and Earth bloom bright. You've wondered about civilizations we've never seen and filters we may or may not survive. It's a lot to carry, not as fear, but as awe. But now the journey is ending, and the story folds gently inward, from galaxies to planets, from planets to you. The universe continues to hum, indifferent and vast, But you get to sleep, to breathe, to feel the weight of the blanket, to notice your heart beating steadily, softly, like a small drum echoing inside a cathedral of stars. Maybe you still have questions. That's all right. The universe is full of them. Questions are what keep us facing outward, eyes lifted, minds open. But answers are not always required before rest. Wonder is enough. There's a softness in knowing you don't have to hold the universe together. It will go on, as it always has, shifting, stretching, flickering, with or without your permission. You're not responsible for the orbit of moons or the balance of equations. Tonight, your only task is to exist, to be still, to let the gravity of sleep pull you inward slowly like a gentle tide. Because in all that uncertainty, all the variables and chaos and risk, you're a constant, at least for now. You are one human, with a name and a history and a place in the story, and even if that place is small, it is yours. Entire galaxies may spin without knowing you exist, but your cat might curl next to your warmth. The plants on your windowsill may tilt toward your window light. Your thoughts leave traces in other minds. Your voice, even when quiet, affects the air around you. And that is real. That is enough. There will always be dangers, some seen, some unseen, but there will also be mornings, cups of tea, soft rain tapping on rooftops, friends who text just to check in, a book that makes you smile, a walk that feels longer than it is because your thoughts wandered beautifully. These are your data points, your evidence that life persists, that in a universe filled with unpredictability, peace can still arrive, quietly, repeatedly. And so, tonight, and every night after this, you're allowed to rest without answers. You're allowed to sleep without certainty. You're allowed to be human just as you are, held gently by a planet that still turns. The universe breathes in centuries. You breathe now, and that breath is your belonging. Sleep well, little Voyager. You've survived another orbit.